All right. As you can see on our schedule, we're going to start talking about molecular and empirical formulas. Up to this point in time, we've been dealing with substances that you know the compound, and you know the amount that we're starting with. In this case, well, what happens if you need to determine what a substance is?
The Lake Area Tech representative is here in the library if any juniors or seniors would like to visit with her. The Lake
So you've been given a known substance. Again, what happens if you need to determine what an unknown substance is? Chances are, I would be led to believe that it's probably easier to know what something isn't rather than knowing what it actually is. And with that, the approach that we take with this class is more often than what I would be led to believe is if you are trying to determine what an unknown substance is, okay, just have to bear with me, and that is typically you would take that unknown substance, use a syringe of some sort, and then you would submerge that in probably distilled water, okay, and then once you've got that submerged in your syringe, then you put it into a mass spectrometer or gas chromatograph, so that's what this machine is. Then you insert that into here, and then you put that substance in, and it shoots a laser through there, and how the amount of refraction that takes place because of the substance you're going through there would analyze what it is you actually have and the percent composition of each one of those. Well, the approach that we want to take is, who can we pick on in here? Okay, so the approach that Mr. Easton has to take is you are taking the stand in a criminal case. Dr. Williamson. Why is everyone looking around like, that's not, just no one was looking around. But so Dr. Williamson, your PhD in chemical analysis or organic chemistry or whatever it is, you pick.
The first one.
Okay, in general chemistry. You're an inorganic chemist, okay? So you are taking part in a chemical trial, and the defense attorney, or no, excuse me, the prosecution would go on and ask, okay, so this substance was found at the crime scene. So it's identified as dimethyl sulfate. Okay, can you explain how you determined that was dimethyl sulfate? Well, see, we take this unknown substance, we put it into a gas chromatograph, what actually measures the percent of each component that's actually in there. Okay, the machine's doing the work, but we've already done a determination on what a percent composition is. So then what's your job then as an expert witness is to say, this is what the machine is doing. Out of the entire sample that I took, the chemical breakdown was this much sulfur, this much oxygen, and then this much carbon and this much hydrogen, dimethyl sulfate of some sort. I just made that up, but it's just breaking that apart in its different associated pieces. Unlike maybe something like potassium cyanide. I think that was on one of your papers, like KCN, the cyanate or cyanide ion. That is certainly a type of poison that it actually is lethal to people because we know A and P people, okay? Sodium and potassium. Why is that important for us as humans? Even mammals, fish, any type of vertebrate. And what does it have to do with a neurotransmitter? What do neurotransmitters cause you to be able to do? Yeah, it has to do with active transport. It allows you to actually contract muscles with the use of that active transport. Well, in the cardiac cycle, as you've seen that where you have those peaks and valleys where it goes beep, 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 beep. What happens is if you have too much potassium from an unknown substance, that can actually disrupt the cardiac cycle. And it'd be fairly difficult to actually determine that unless you could actually do that with a lab apparatus, and that's what you're testifying to. So now, who's not getting away with a crime in here? Who's not getting away? Okay, so you got him. You explained it just right, Dr. Williamson. Okay? No further questions. You may go home now, play in your Nintendo. I don't. Regardless. I don't think you want to mess with this young man, just on account of he knows his chemistry.
What?
That's not what you want to say on the stand. Yeah. Okay. Anyway, so page 245. So what you're doing is you're actually explaining how a piece of lab equipment actually works, but you're explaining it mathematically. Okay. So when a new substance is synthesized or discovered, it is analyzed quantitatively to reveal its percentage composition, which we know how to do. You mathematically did that. You take 80 grams of barium carbonate. Well, how much oxygen is in that barium carbonate? You would break it up into its associated percentages. For these data, from these data, shouldn't it be this?
Probably.
From this data, the empirical formula is then determined. An empirical formula consists of its symbols for the elements combined in a compound with subscripts showing the smallest whole number ratio of the different atoms in the compound. For an ionic compound, the formula unit is usually the compound's empirical formula. For a molecular compound, however, the empirical formula does not necessarily indicate the actual numbers of atoms present in each molecule. For example, the empirical formula for the gas dibromine is BH3, but the molecular formula, however, is B2H6. In this case, the number of atoms given by the molecular formula corresponds to the empirical ratio multiplied by 2. Now, that doesn't mean anything to you right now, but it will. That's where, see, we can pick on you ladies, where your guy, if you're dating your whatever, they tell you your 2 favorite words. Guys, what should their 2 favorite words be? Has something to do with trust. Trust me. Those should be your 2 favorite words. Right, guys?
Oh, yeah.
Ladies, is that true? Trust me. I don't know. It just sounds good. All right. So calculation of empirical formulas. To determine a compound's empirical formula from its percentage composition, begin by converting percentage composition to a mass composition. Presume, I don't like to say assume, so presume that you have a 100-gram sample of the compound. Then calculate the amount of each element in the sample. For example, the percentage composition of dibromine is 78.1% boron and 29.9% hydrogen. Therefore, 100 grams of dibromine contains 78 grams and 21.9 grams of hydrogen. Next, the mass composition of each element is converted to composition in moles by dividing the appropriate molar mass. So we're not going to bore you with those details. You're just taking prior knowledge, taking grams of a substance, and converting it to moles by using a molar mass. So for instance, when we got 78.1 grams of boron, where did that number 10.8 come from? Do we just make that up? Yeah, the atomic mass of boron is 10.81. So then 21.9 grams of hydrogen is divided by 1.01. Again, the atomic mass or molar mass of that element or substance. Okay? So I don't want to go too far into molecular formulas because those are just a little more tricky than the empirical formula. But that's something that we will get to maybe as early as late tomorrow or on Wednesday. So is it worth your time for us to read together the sample problems? Usually in the past is what I would say is, okay, there's sample problems on page 246 and 247. I usually just leave that up to you to read through because you can do that on your own time. It's the practice problems that we spend time on. Would you agree that if you really want to spend the time on it, you could read the sample problems yourselves and work together on the practice problems? Okay, so then that is what we will do. Okay, so one of the practice problems we see on page 247, and it's on the bottom. So again, you're taking prior knowledge, you're taking grams of a substance, and you're converting to moles. And that's all you're doing at this point in time. Okay. So, get this erased. I should have done this earlier. We're burning daylight here. So practice problem number 1 on page 247, sorry. A compound is found to contain 63.52% iron and 36.48% sulfur. Find its empirical formula. Notice when you have those percentages, they both add up to what? 100. So every time you're given a percentage of some nature, you can presume that it's going to add up to be a 100% solution. Now, the paper that you had handed in, you said, I added them together and I got like 99 point something. Does that sound accurate? Oh, okay. I thought it was on like the last, well, okay, it doesn't matter. So we got 63.52% of iron. So again, you can take that percentage, you change it to grams. Okay, and then what was the composition of the, not oxygen, it was sulfur. What was that? 36.48 okay, grams of oxygen. Now, for some people, I got that in my mind. I just want to see if you're paying attention. Okay? Oh, yeah. Just right after dinner. Now, when you're doing these, you are really going to do yourselves a favor when you actually label this, okay? Because otherwise, if you have a question, I'm trying to help you and you're not showing these labels on here, how do you know what it is you're actually dealing with if you just put 63.52 grams? You actually have to take that extra little bit of effort and label what it is you're doing. Okay, so with that, how do we cancel out this next step to get to moles? Okay, the atomic mass. So 55.85. Trust me, by the end of this year, you'll have these numbers memorized too. Maybe you do already.
No, I got too dumb.
Well, that's not the spirit. Say you're too dumb.
That's the spirit now.
Oh, okay. Well, what do you do when the Christmas spirit shows up? Oh, all right. So this gives you a mole of iron. Remember, every time that you, on the periodic table, give that a number of the atomic mass, that gives you 1 mole of that substance. It's just a counting unit. So in this case, you're going to get, what, a little over 1 mole of that? About, because if we started with 55 grams of iron, well then we're going to get 1. So 55 divided by 55.8 would give you approximately 1. No one could argue with that logic, right? Okay. So when you divide these out, okay, 63.52 Okay, so 1.13, so we're going to say 1.12. See, this is where I get to cheat, and I can say we're supposed to get FES. Okay? Well, it sounds pretty simple. Well, yeah, it maybe is. Okay? So then, what do we do here? How do we get this to moles of sulfur? Yeah, same thing. For every mole of sulfur, get 32, what, 0.06 maybe?
Yeah. 0.7.
So upon doing that, that's also going to give you probably 1.13 maybe, I don't know. I just was under the presumption that someone was doing that. Okay, this one's 1.14 mole. Maybe. 63.52 divided by 55.85. Oh, yes. Yes, it does. 1.14.
That's a pretty easy ratio.
Okay. So now what you need to do is you find the smallest number of the moles, and then you divide that into each and every one of them, because sometimes you may given 4 components of a formula. So that's pretty easy to see. The smallest one is 1.14. So when you do that to everything involved, it just comes out to 1 each. So there's 1 atom of iron and there's 1 atom of sulfur. That is your answer. The tricky part about this will possibly be, and it's easy to make a mistake, we get to this point and we forget to do that last step of dividing by the smallest number of the moles. So pretty straightforward. Any questions on this? Can we erase that? Okay. You know, everyone's sitting there yawning. I wouldn't think that would be the case with all the trick-or-treating we probably did last night. Or didn't we do any trick-or-treating?
Do you have a lot of trick-or-treaters?
50.
Really?
Yeah.
Cameron's family didn't have one. Really? Is it? We had 90.
We had like 3.
We had 90. Other than
No.
like
My mom
family,
counted.
just said they did not like they did not have one.
No, we're one.
Oh,
People don't go over there.
They were all
That's-
But still,
probably
we
at
Oh, yeah,
2
sure.
or 3.
that way? Okay.
Everyone goes with it.
So you got like rich people.
Does this take part over that way, overseas? Do you do trick-or-treating at used to? Would you still have done that?
I could have came. One thing else.
Okay.
We didn't have one person that wasn't related to us. We just had like bad history.
Okay. Then we're going to do practice problem number 2. Then by that time, it'll be enough for today. Okay. So, this one's a little more tricky because there's that extra added element in there. Because it says, find the empirical formula of a compound found to contain 26.56% potassium, 35.41% chromium, and a remainder oxygen. Okay? So here's where you got this fancy lab apparatus, and it says, okay, we've got some potassium in there, and we've got some chromium, and some oxygen. So we know that that's what's in that unknown substance. But what's the actual chemical breakdown of that? Well, we really don't know, okay? So to mathematically do that then, doctor,
Sorry, I was spaced out.
I can tell. You can't do that on the stand. So doctor, what do we do? What did we do in the first example?
Take 100 minus.
Throw her in the gas.
Okay, you're about 3 steps ahead, which is better than being 3 steps behind. I get that. You do need to convert them to moles, like you just said. So if we have, what was it, 56 something percent of, no, 26.56% potassium, which means we always can presume that it adds up to 100%, okay? So 26.56. Now, it's not percentage of potassium, rather what instead? It's not percent of potassium, it's grams of potassium. You just change that percentage to grams, okay? Okay? So then, how do we go about doing this? Just like what we've been doing since last August. For every mole of potassium, how many grams would you get?
39.1.
Okay, so that gives you a specific number of moles of potassium. Okay, then the next one down. What is it that we actually have for chromium? Oh, okay. 35 point what? 01? 41. Okay. Again, grams of chromium. So we're a little ahead of ourselves, which is fine. For every mole of chromium, there's 52 grams of chromium. And then that gives you your amount in moles of chromium. Now we got this last one. Okay. But it doesn't say how much there is. Okay. Which means you're going to do what with these two numbers? Add them together and then subtract from 100. Okay. So upon doing that, 26.56 plus 35.41. And then you can just subtract 100. It's going to give you a negative number, but it's still the right answer. 38.03. 38.03 grams then of what's left over, which is oxygen. Convert that now to grams of oxygen. Awesome. Thank you.
I got them all. I just don't know how to write it at the end. Like where?
So how do we, just a moment, how do we convert this to grams of oxygen? Now for those of us just joining us.
Divided by 16.
Okay.
So I take your mass divided by the atomic mass per mole.
Okay. So for those of you who are just joining us, we're reading practice problem number 2 on page 247. So in short, it's telling you that this unknown substance, it contains potassium, chromium, and oxygen. These are certain percentages that were given off. It had 26.56% potassium, 35.41 percentage of chromium. In every sample that you're dealing with, the percentages can only add up to 100. So that's why we added these two together, subtract from 100, and it gives you 38.03 grams of oxygen. Then with the use of the periodic table, you need to get these into moles of each substance. So can someone pick the top one here, please? And give me the number of moles of potassium. 6, 8?
Yeah.
Okay. Can someone do this one for me, please?
6, 8.
Okay.
2.38.
Okay, so again, this is something that we can track all the way back to last August. Okay? But we can't shoot this. This doesn't come out to a 1-to-1-to-1 ratio like this first one did. Okay? You can't say 0.68 moles of potassium and chromium and 2.38, or I mean, what I'm saying is you can't use this as your formula. And then, what was this one? 2.3. So that does not work. So now you're 3 steps ahead of us. How did you come? You're right when you came up with those ratios. How did you do that?
Divided the 2.3 by 0.68.
When you get to this step,
Well, those are just going to cancel out.
right, you have to find the smallest one, okay? So therefore, in this case, 0.68, 0.68, 0.68. And as you had correctly said, these are going to cancel out to just 1, which is true. 1, 1. So we're getting a little closer. Do you suppose, could we write the chemical formula like 1 to 1 to 3.50? The answer is no. They have to be a nice whole number. It can't be on a quarter. It can't be on a half. It can't be on a 3/4.
227.
Okay? So what that means then, if you double each and every one of these, you change that to what you had just said, K2Cr2O7. That's correct. Now, one of the reasons that something like this is really important, if you are dealing with K2Cr, is it 07? No. I want to say it's 03, okay? That's potassium chromate. This is potassium dichromate because you have 2 of those together. For those of you next year, when you take, have you had any organic chemistry at all? Let me give you, well, we'll come back to that. Can I erase this for those of you who have wrote this down or chose to or are following along? So for those of you who went to visit Lake area, if you choose, you can come back and explore this. Okay. See, I got to think about this myself. Something like that look familiar. Compounds that are just carbon and hydrogen and oxygen. None of that. Okay. So the reason that that's important is for those of you who take this next year, this is such a powerful oxidizing agent. That reaction, it continues, and it continues, and it continues until it runs out of oxygen. Okay? It used to be that there's certain types of munitions or rounds. They actually continue to burn inside the human body as long as they have oxygen. And I can't imagine how painful that would be. You have some of those types of rounds, okay? This is during wartime, we would think. Penetrates the human body, it's exposed to air, and it burns and burns and burns and burns. And you get the idea. It continues to burn until this guy finally runs out. How many of you, what I want to say, remember, what was it, Hunting the Elements a couple years ago in, we had that David Pogue, I think. He was the host on that show. And again, typically what this does, he was a glass bowl of water, dumped sodium in there, it's a little bit of an explosion. You dump potassium in there, and it's much more volatile. So the same thing again happens when that potassium is exposed to, well, you could say, I thought you said exposed to air. Well, that's true. What do we have in air? Oxygen. Well, if it's in water, is there any oxygen in water? Yes. So that continues to burn and react until it finally runs out of oxygen. So determining these formulas, that's a really important deal to actually identify what a substance is. And that's where Dr. Williamson testifies on the stand that that's what's actually happening. So the criminal, you're daydreaming again.
Yeah?
Because all of a sudden you're looking that way, all of a sudden you look forward. So that's where you testify and the criminal does not get away.
Yep.
Okay. All right. So that's a little over about 31 minutes now. Left side, we okay with this? You might not know. For those of you who were here, how about we say that? Okay, middle for those of you who are here. We're good. Right side. All right. We'll pick up with this again tomorrow.